So you remember I told you basically that the microcapsules can release a limited amount of material, but they can be very well dispersed. On the other hand, microvascular networks are very large, and you have to replace a lot of load-bearing materials to have them in your composite. Well, kind of, and there were a few approaches to uh, limit the adverse effect or the disadvantages of these two systems. In my opinion, one of them was when they were using electrospun fibers for self-healing. In this case, the fibers were core shell. So basically, the shell is a solid material, and the core is the healing agent. Now you can have two types of nanofibers or microfibers. One with healing agent, the other one with the cross-linking agent. And so both of them have the shell. They're made through coaxial electrospinning, basically. It's similar to electrospinning, except that two polymers are fed through the syringe. One that goes on the outer layer, the other one that goes in the inner layer. The outer layer, in the outer layer, the solvent evaporates. You will be left with the solid shell. The inner layer is the healing material that remains in the liquid before the reaction starts. This is like the tip of the electrospinning. It has the outer layer, and the inner layer goes in, it becomes a fiber. Now, the reason I say it could be better than conventional microcapsules is because now you have a web of microfibers or nanofibers that you can just put into the matrix. And yet it has the continuity of the vascular network that can release a considerable amount of healing agents. So, but keep in mind that these fibers, as you can see here, the inner diameter of these fibers here is extremely small, which means the flow of the liquid, of the healing agent inside them, is not substantial, the Poiseuille law. So, but regardless, it has some, the liquid in the vicinity of, if the crack happens here, the liquid in the vicinity of this guy can still go out by capillary forces and does the healings. So these are two components, fluorescent, different colors, just to show that the two components can be released. The same color code applies here. And here, they show that if there's type A, the crack on the surface will not be healed. If it's type B, crack will not be healed. If there's no fibers, crack will not be healed. However, if you put type A and B, the healing agent and the crosslinker, actually the crack does seem to get slightly healed. So for instance, compare this region with this region. There's, or like this region with this region. There's a line here, and this line is almost absent here. So it can be used for this purpose. Oops. Now, another work with respect to microcapsules and microvascular networks was using the combination of them. And the reason for that was because people were trying to combine the advantages of them and get rid of the disadvantages. Microvascular network allows for large volume because you can, if the crack happens here, you can have liquid from all over the tube, even feed it from outside the composite into the region. And if you have microcapsules, as I explained to you, you can make them, disperse them much better inside your matrix. So you can basically use microcapsule to heal small cracks and use microvascular networks to heal very large cracks. An example is this guy, a large crack that was accessed. So basically this blue and blue and the red line you see is the supply lines of the two components of the healing agent and the crosslinker that were fed into this hole. This hole was generated in the composite by an impact in the lab, and they fed everything to this, and this is the schematic here that the material was healed. So the key here is to consider healing at very different length scales. Smaller and smaller cracks can be healed much more efficiently with microcapsules because microcapsules are much more dispersed, and they have a small volume of healing agent in them. But larger cracks, and a small volume of healing agent is all it takes to heal small cracks. But larger cracks, you need a lot more material to be fed in. And so you need you need a lot of healing agents. Now, large damages means you can afford to have these vascular networks farther away from each other. And yet when a large damage happens, there's a good chance that it will bump into one of these guys. It will puncture one of these microvascular, these veins, and release the healing agent. This concept has been demonstrated in the lab, as far as I know. But a summary of everything that I said is in this paper here that was published rather recently. It was 2018 paper. The idea was to mimic nature, to do self-protection, self-repair, detect damage and do the self-repair, and even regenerate. I will explain each of them shortly. But the idea for self-protecting is y-axis is the performance. You remain at your 100% performance by self-protecting. I'll explain how. When the damage happens and your performance goes down, you detect it, and at some point you trigger a healing mechanism. When the damage is huge and you get to lose material, you regenerate and you come back. Okay, that was basically the idea of a very visionary paper that came out. Now, when you look at it, how did they do it? You know a lot of the components of it. Self-reporting. The example we talked about is basically this one, chemical reactions that change colors. But the other one that we haven't yet discussed, but we will discuss in the context of nanocomposites, is change in electrical conductivity. If there's a damage in your conductive material, it disrupts the path of electrons or ions. And so that leads to a change in electrical conductivity. These are the signals that can easily be picked up, especially electrical conductivity. Because we would like to be able to measure everything in terms of voltages, because voltage can be transferred to, because voltages can be monitored easily, can be connected to a monitoring system, and can also be used as a function, as a part of a feedback loop to make changes and compensate for the damage. Self-protection. We talked about autonomous coatings that prevent chemical damages to a structure. We talked about it. So here, the coating is used to protect the metal that's underneath. And if coating is damaged, the metal underneath can be damaged. But if the coating gets healed, it prevents the damage. The other thing we learned about is the smart heat transfer. basically the barrier, heat barrier coatings that we talked about that takes heat from the higher temperature areas of the material. We talked about self-healing at length. Examples are here or even here. And last but not the least, the regeneration. The regeneration, you may think of it as self-healing, but the main difference between self-healing and regeneration is the volume of the material that's being added. Typically, regeneration means a chunk of the material is removed. When there's a crack, no material is removed. There's just a crack opening. But regeneration, let's say through an impact, a part of the material is removed. So then new material needs to be added there. An example of the regeneration is basically this concept here. So I highly recommend reading this paper to you. Read it the way you would read, slightly it's a science, it's a visionary paper again, that's the best way to put it. And I really enjoyed reading it, but it's not going to be part of the exam. Okay, so this is the last video of this section, and I will see you again in nanocomposites. Thank you.